Hi everyone, I would like to welcome each one of you to today's talk about asteroids. The speaker is a postdoctoral researcher at INAF, Astronomical Observatory of Rome. His research interest focuses on VIS, IR spectroscopy and spectrophotometry of small bodies in the solar system. He has worked with ESA's Rosetta and NASA's OSIRIS-REx space missions during his doctoral and postdoctoral studies. Dr. Dash obtained his bachelor's degree from University of Colombo and his master's degree jointly from University of Science and Technology of Hanoi and Observatoire de Paris. His PhD was conducted at l'ESIA Observatoire de Paris and was awarded by Université Paris Diderot, Université Sorbonne Paris Cité. As usual, there will be a Q&A session after the talk. So if you have any questions, kindly leave them for the end. Before I mute myself, I'd like to thank Dr. Dash for joining us today. Dr. Dash, the floor is yours. Enjoy.
Yeah, thank you very much. Are you able to hear me clear?
Perfectly.
Yes.
Yeah, okay, yeah. Thanks for inviting me in the first place. And thanks for the introduction as well. So today, in this context of Space Week, I'll just give you a brief introduction about asteroids. So the very basic, nothing too fancy. Okay, so let's get started. And yeah, so asteroids, what they are, I think you probably have some idea what they are. This is just a basic briefing about asteroids. So these are the remnants of the formation of the solar system. So these are the objects that witnessed the beginning of the solar system and that did not end up becoming planets like the planets we know, like the Earth, for example, due to various reasons. So here are some images of asteroids visited by spacecraft. So these are not the telescopic images, but yeah, the first asteroid, for example, was discovered about 200 years ago, and for now, like we got like close to 1 million asteroids being discovered at different sizes. So yeah, basically these are compositionally made of rocks and especially of silicates and organic matter. So here we're seeing the biggest asteroids here is about the it's 4 Vesta. This is the second largest asteroid in solar system, and it has, interestingly, the highest mountain on solar system due to a crater formed there called as Rhea Silvia. So yeah, so and asteroids, but they're not. So they're not comets nor meteorites. So basically, comets are the objects that were formed as opposed to the asteroid, which were formed inside the, let's say, in the closer parts to the sun. But these were formed much further away from the sun. So they contain more material because, as you know, in the formation of the solar nebula, as the sun formed, the inner parts were much hotter. So the objects that of cometary nature could not condense in this area. So this is like a defining area we call as the snow line. So the matter that condensed a snow line of which is referred to as the condensation area of water molecule, so H2O. So the objects that were much let's say the objects like silicates and metals, they get condensed inside the snow line, and beyond the snow line get condensed the volatiles and these components that contain that the comets contain. So these objects are highly volatile, and sometimes they get their orbits perturbed, and then they come to the inner part of the solar system, and that's when we are able to see them with this very bright comas and the tails. So I think some of you might have already seen a comet. We were lucky to see a comet last year, the Neowise comet, which was present for like a few months. And yeah, so these are not, we are not talking about the comets today. So here are some images of these comets and also some meteorites. Meteorites do come from asteroids, but they are fragmented pieces that end up on the Earth. So in a way, they have a direct correlation with the asteroids, but they should not be mistaken for asteroids themselves. So as we move on, so here is a classic image. You know, this is nothing is to scale here. So just to give you like some idea about the planets, just for like a beginner's view. So where they are asteroids, they are basically originally located between the orbits of Mars and Jupiter. As you can see here, these are small rocks like objects are the asteroids, and they are not alone only there. They got even closer because of this very interesting dynamics in the system. Because of these objects are not spherical and they have irregular shapes. They get torqued by themselves from their thermal emission, and because of this, there's a force known as Yarkovsky effect, which lead them to change their orbit. So their same major axis, so distance from the sun, every distance from the sun would increase or decrease depending on their retrograde or prograde rotator. So in this case, they would migrate in the orbital plane, and then they would arrive to these resonance areas with giant planets, for example, with Jupiter or Saturn. And in this case, they could get kicked out from these areas and then arrive in the inner part of the solar system for some of them. And some of them go away to the further parts of the solar system. So once we see as the near asteroids are the ones that come originally from this system that get kicked out from through the areas of resonances. So here is an area, probably you heard about these Kirkwood gaps. So these are the, if you see the image you are seeing here shows the number of asteroids for a certain amount of distance. And on the x-axis is the distance from the sun, every distance, so the same major axis, not to get too technical. So these are, so you can see some gaps where this density is lower. So around 2.5, 2.8, and close to between 2.9 and 3. So these are like empty, very like less asteroids are there because of these dynamical resonances with giant planets. So the asteroids could not stay there. As soon as they arrive to these areas due to the Yarkovsky effect, they get pushed away, and so they arrive towards the planets. They could arrive towards planets in the inner parts, towards Mars, Earth, and so on. So yeah, so here's a wider picture about everything. So I think you heard about the whole solar system being contained inside these old clouds, so-called of this giant structure of cometary nuclei, which were the objects that got kicked out during the initial phase of the solar system due to the dynamics, and they ended up there. But we don't see the objects there. We decipher their existence from the comets, long period comets that arrive from different directions. So these were very initial discoveries in the 1950s using the Whipple's models of the solar systems, the comets, and they are. This is how we infer from this existence of the old cloud, because they are so small objects and so far away we can observe them from the Earth with the current technology. So, and then you have these, if you come closer to the system, you have these inner parts of the solar system and the outer part. So yeah, so it's a very giant structure, and that reaches out to about close to 100,000 astronomical units, whereas the Earth is located at 1 astronomical unit. Okay, yeah, as I told you, these small bodies, comets and asteroids, are the witnesses of the early solar system. So what can we learn from them actually? Here are two images. On the left, you see the sort of an evolution of a planetary system. So here you are seeing the nebula, or initial nebula, about 4.6 billion years ago. So you have this sort of a disk, torus shape, flattening to become a disk around a proto-sun, which would become a sun later. And then you get this sedimentation, or these grains being condensed and forming a compositional gradient defined by the thermal gradient of the solar system. And then there's all the dynamics taking place, and then the protoplanets start to form, and then you are seeing currently, for example, in the solar system, the giant planets and the small planets. So this is not always the case. You could form these systems differently, as we've seen in exoplanetary systems. So here you are seeing on the right some images are taken with the ALMA, where you could see a nascent planetary system where you see a planet has already formed, a protoplanet, and it's feeding from its neighborhood. So that's why you see a gap, and those are the dust in the area. So these are very interesting. But what we have in our hands is solar system, because we lived here and it's closer to us, so we could study it better than the other systems. And we could have to also keep in mind that we could be biased because we have our own system, and it's also important to have a global view without being biased from our own advantage. So yeah, so as I told you, this snow line, defines the areas of condensation for different material. So if you think about the asteroids, we could classify them as spectroscopically S complex and C complex. So the S complex contains more or less silicate material, and you could see some of the spectra here. So these are the S types, SA, SQ, SR. And the C complex, which contain organic material, carbon-based asteroids. So these were formed away from the snow line, because this component could not have, in the first place, in the initial part of the solar system, it could not have condensed inside the snow line. So these are more primitive bodies, and this is why we are interested in terms of studying solar system, to focus more on primitive bodies, to understand the origin of these bodies, and for example, what they really were, because the planets, we can't see this original stuff because the planets are processed through for example, planets could have geological activity, volcanic activity, and they're differentiated, so you can't see this stuff. So that's why we are interested in studying this more pristine material that is present in the primitive small bodies. Yeah, so again, these are a bigger wave of the same plot I've shown in the previous slide. So this is the spectrum so here, for example, you have from 0.45 microns to about 2.45, going from visible to near infrared part, and this tells you the composition and what they are primarily made of. And from this, we could learn many things, and we could even choose a target for a space mission to send if we are interested to know how the life, for example, because we know the life is based on the organic material and carbon, and how will this first material that evolved even into being life forms before the life began on the Earth. Yeah. Again, here is the plot that shows you very confidently the closeness in terms of the Waters D to H isotopes ratio, and also the nitrogen 15 and 40 ratios. And if you do this for the these meteorites that come from primitive bodies, so these are different special type of meteorites which are called carbonaceous chondrites. So these are the meteors that contain these small spherules like made of carbon-based chemistry, and these plot very close to the parameter of the Earth. And you can see the comets, they do not really converge towards the Earth. We have several measurements of the comets and also the solar value here. So this is a very strong constraint on carbonaceous chondrites and indirectly on the primitive bodies or the C-type asteroids that it's very close to the, that's what they've actually come to the Earth. So on the right here is an evolution plot showing the evolution of the solar system and the mixing of the bodies. So you could have asked, because I said that these the asteroids that were from, we could even see on the in the inner solar system the asteroids that contain organic material. So if I say like they get thermal process and they condense much further away, how come they are there? So this is all due to these planetary migrations. So these is explained by the migration models of the planets. And as you can see here on the red and blue colors, you can see this evolved material on the red forming close to the solar sun, so close to Jupiter, let's say. And the blue sort of material that's condensed, and these are the volatile primitive material that were not processed thermally. And so this is about 700 kilo years. So it's a very early solar system. And then on the top here, and the time evolves to the down, yeah. And then you see like 100 kilo years, and just 0.1 million years from the beginning. So there's this migration of Jupiter towards the inner part of the solar system, and then the Saturn also formed and got migrated towards, and there was a torque exerted from this imbalance of the gases, and then they migrated back towards, and doing so they populated these inner parts with the blue material and the outer part with red material. And so these are these were the culprits for doing this sort of mixing in the solar system, and that's why we see the material with very primitive composition even in the near Earth space, also in the asteroid belt. And also we could see also these Jupiter Trojans. These are the asteroids that are constrained in the Lagrange points 1 and 2 of 4 and 5 of Jupiter. And these are the families of asteroids that are compositionally very primitive, containing mostly D and P types of asteroids. So here is these image again. So on the y-axis is the eccentricity. I forgot to tell you. So these sort of the orbits get very eccentric, and that's how they end up close to the solar system's inner part. Yeah. So all this has a very interesting correlation with the life formation on the Earth. So these are the cyanobacteria that formed at the very initial phase of the, before the prebiotic life on Earth. These planetary migration models, so the Nice model and the Grand-Tact model, they end up predicting the late heavy bombardment. So this is like a lot of bombardment of asteroids and the cometary nuclei towards the Earth and inner planet of the solar system that took place about 4 billion years ago. And this is also we find evidence for these cyanobacteria and these stromatolites this stuff produced by these primitive bacteria in Western Australia and also in Greenland. We could find evidence, and so we think is a result of this bringing of material, because Earth was very hot in the beginning and it could not have volatiles, and the influx of material brought this material necessary for the Earth's life to emerge at a certain point. And yeah, so this is why we are also interested in another reason why we are interested in asteroids, because of the life formation on the Earth. So the life as defined, it could be having different characteristics. So this is a Wikipedia definition I just took here, which is taken here. So you could define life as a certain form, and the chemistry of life, as you know, is based on on the carbon and hydrogen elements. So so this is very interesting, because this is exactly the material of the asteroids contain, actually, because they also contain water in the form of phyllosilicates, for example. They are inside the asteroids, but not at liquid bottom, of course, combined with other rocks to form minerals. And yeah, I would not go too much into details. So these are the chemistry of life here. Just giving you some insights, like the importance of water, because it's a good solvent, and it's very has many properties that favor the development of life. So yeah, and also the carbon. So these are the four main abundant material in the universe. So after hydrogen, helium, oxygen, and then followed by carbon. And yeah, these are able to form very long bonds, actually, and also make some amino acids. Yeah, and also silicon, on the other hand, has a weaker bond. So in solar system, we don't find in life as you know it is not based on silicon here. But yeah, so these are some ideas about this chemistry needed for the life and how they are related to the asteroids, because the asteroids contain this stuff, and we could see from the material that have on the Earth in terms of as meteorites, we could find even amino acids. So this is a very promising towards probing towards this interesting question of the emergence of life, and also the DNA is also made of this chemistry. Yeah. So here is the Murchison meteorite, so which is carbonaceous chondrite, and it's has a very interesting amount of 12% of water content, and it has contained a high repository of amino acids. So we discovered this kind of carbonaceous chondrite asteroids, and we could even link them spectroscopically with the observations we have towards the C-type asteroids or the B-type asteroids, which is a part of the C-complex asteroids I've shown before. And now we have two space missions. One just completed its first part of a space mission. So I think you might have heard of these two missions. The NASA's OSIRIS-REx space mission that visited Bennu and collected a sample from its surface, and it's returning its sample to the Earth in a couple of years. And then there's JAXA's Hayabusa 2 that visited the Ryugu asteroids. Both are C-complex asteroids, Bennu being a B-type asteroid, which is, as I told you earlier, just to repeat, it's a sub-category of the C-complex asteroids containing the organic materials. And the samples of the Ryugu were already delivered in last December. And the first results are going to be published very soon. And we are expecting for very interesting results for this mission. And yeah, so these are two missions that aim to collect some asteroid sample and primitive material from this organic or from this carbonaceous asteroids, and bring them back to the Earth. So I have the privilege to work with the NASA's OSIRIS-REx sample mission, and to find the place which ended up to be the Nightingale crater, from where we collected the sample. So I was taking part actually in the process of selecting the sample site on the asteroid Bennu during these 2 years. Here is a picture of Bennu. As you can see here, is a very small. It has a diameter of about 0.5 kilometer, and you could see it's very rocky surface. A lot of boulders, and there are some craters. And it was very hard to find a place where the asteroid could securely get the sample without any problems. So, which we did finally. So, and here is Ryugu. On the other hand, it's a bit bigger, and it has also very interesting structure. It has craters on it, and as you can see, both of them have sort of this equatorial ridge. That's because of their spinning up to this Yorp effect. So this is also due to the thermal emission of the asteroid. So the material from the poles, they would come close to the equator, and because of the centrifugal force, and they would make a bulge. And so this is something, if you are careful about this morphology of the asteroid. So here I'm going to show you some images from the sampling of the event. So to sample Bennu, there was a rehearsal before the sampling took place in October last year. And so the idea was to come to surface the target area, and then just get closer, and then backfire and test how it goes, and then finally do the sampling. So here on the right is an image taken at about 70 meters above the surface. And the image has about 2.5 centimeters per pixel. So it's a very detailed image. And the sampling area is to the left here. And the limit is the crater, the Nightingale, delimited by around this sort of an arc. So it was sort of going towards this area. But this was just this sampling rehearsal. And here you can see, I hope you're able to see the video of the real sampling event. So yeah, I will show it several times just to get to see what happens. Actually, this is this very porous and loose material. As soon as they get sort of an impulse, they would displace themselves, and you could see the trigger of this sort of particulate material on the surface from this impact. So some of this touchdown actually. So what you're seeing here on the circular mechanism on the is what we call the tag SAM, is the touch and go sample acquisition maneuver mechanism. So which has a diameter about 30 centimeters, and which collects all the particles as soon as it's touched. And so this was very interesting, exciting experience. And so here, this is quite a slow motion image, as you can see in more detail, the types of rocks and their nature, and their distribution even. And you can do a lot of science with only with these images. Yeah, okay. Now let's talk a little bit about the risk of the asteroids. So as you know, there are a lot of asteroids, and as of last February, we have about 20,000 near-Earth asteroids. So these are the objects that get close to the Earth, and about 2,000 of them are, let's say, about 10% are potentially hazardous asteroids. So they have a very low minimal orbital intersection distance with the Earth, and they are sufficiently large enough to cause, if impacted, a regional damage or local damage considerably. So these an update on this number is about 2005. So like, as you can see, we are discovering more asteroids day by day because we have more observing capabilities than in the past. So during this tour, let's say a year and a half or more or less, we got about 5,000 more asteroids, near-Earth asteroids, yeah. So these asteroids can be categorized into 4 types. So these amorphs, Apollos, Athens, Atiras, depending on their orbit. So most of them are Apollos and amorphs, and very have a few Atiras. So they all depend on how close they get to Sun and how far they get the Sun in their elliptical orbits, and if they cross Earth's orbit or not, or that of Mars. Yeah. So talking about the risk, we have a scale which is called the Torino scale to measure the danger of the asteroids. So it grows with their size, and so this directly corresponds to the energy that they could give to the Earth, to the impact actually. And also, if you can see a probability of the collision, so you are able to give a classification depending on this Torino scale. So the number 0 here corresponds to about, let's say, is a differential selection, let's say, because even the sizes of objects of 5 kilometers of diameter, if they have very low probability, they would be 0 risk. But as soon as they start to become, let's say, 1 in 10,000, then it would be quite important, and they would enter to the number 1 danger. And if even the risk gets greater, if the probability is more, so about 1 in 100, and if it's 1% of probability, so 1% of probability, it's if you are seeing here in the blue lines 2 and 4, 3, this could be considerably dangerous. And if you go to 6, 7, 8, even the smallest bodies like 20 meter bodies with high probability risk would create a very damage, and it could even, as size grows, you can see the catastrophe could be global even. So we had to be very careful about this astrology, as you know that they helped us to have the life on the Earth in the first place, but still, like, there is a threat of from them to create a danger and do a catastrophe on the Earth. And also, if you think about a comet, if a comet were to impact on the Earth, apart from the asteroids, the impact would be even bigger because the comets have higher velocities near their perihelion. So the comets would come even at higher velocities than the asteroids. So here we have 5 kilometers, but the comets could even go to like 20 kilometers per second. So the catastrophe will be even more disastrous. So here is an event that took place in 1950s. There was a lady who was in the States lying on a sofa, and then a meteorite fell through her ceiling, and it created some damage onto their ceiling, and it just bounced on her. So there are no records of asteroids being or meteorites being fallen on people so far, according to the records we have. But this could give you an idea of the danger. So here is this Chelyabinsk meteorite that took place, that happened in February 2013. So this is an asteroid about 15 meters that exploded at at a height about 30 kilometers from the surface in the north of Russia. And it led to a shock wave that destroyed a lot of buildings and damaged, and it led to a local problem, thousands of euros of problem. So I have video, I can't play it here, but yeah. So here is another impact from an asteroid, about 50 and 100 meters of size, and that arrived at the Siberian forest in 1908. So this was a large forest area. About 2,000 square kilometers were destroyed, and if you place the same area on the city of London metropolitan area, you could see it's very big area, and I think you could imagine the disaster it would take place if it landed on a metropolitan area. But it was on a forest. But yeah, all the animals had to suffer, but not the people in a city. And also we can go back even 65 million years ago. So we can we have this Chicxulub crater in the Yucatan Peninsula, which led to the disappearance of dinosaurs. And it's very ironical because of this, I think that led to the betterment of the mammals, and then humans could develop thanks to an event that, or due to an event that was of extraterrestrial origin. Yeah, so this is the things that asteroids can do. So what we can do if we detect an asteroid would come on our way. So we have some solutions in progress, let's say. So the European Commission has financed some projects in the last decade to address this problem, to give some solutions. So there are sort of three areas we can explore: the gravity tractor, kinetic impactor, and in the worst case, the nuclear deflection. So all depends on how early we detect the asteroid that's going to hit us. So if you know it's coming from a very long time, about 100 years, you can use this gravity tractor project. So you send a big mass of an object, a spacecraft with a lot of mass, and you keep it orbiting very close to this asteroid. So over the course of the years, its orbit will slightly get changed, and then you could the orbit intersection would not take place with that of the Earth when the Earth is there. So the kinetic impactor is an idea that you send an impactor to the asteroid in question, and then it leads to a change of its orbit. Which would eventually lead to a change of its, which would lead to avoiding the impact with the Earth. And in the worst case, if the object is very large and we do not have a lot of time, the problem is to avoid very huge catastrophic area on a global scale. But let's opt to have a smaller local problems, because if you use a nuclear solution, it would lead to thousands of debris or even more. And then we can predict the orbits of these debris, and we could imagine some of them would land in the Earth, but the tragedy would not be as catastrophic as it would have been if it were once a big object that impacted. So in terms of this kinetic impactor, we have a mission in progress. There's a DART mission from NASA that will be launched in a couple of months, and we should go to the Didymos system. So this is a binary system. So this is a Didymos A, the asteroid that is orbiting Sun, and it has a companion, a satellite asteroid, Didymos B, or the Didymorpheus, that is orbiting. So the objective of this mission is to impact a spacecraft, so the DART spacecraft, on the on the Dimorphos satellite and see how its orbit would change around its main asteroid in its binary system. In this way, we will be able to characterize how we could use in practice on an asteroid that is potentially hazardous and which could impact Earth on one day if we were to develop this mission successfully. So the idea is also, as the spacecraft impacts, there will be a cube set which is called Lichia cube, which I'm just starting to work on actually, to observe this event and to characterize the impact. Yeah, and there'll be also a European Hera mission that will come a few years later to observe the impact. Yeah, also there's also interest for the asteroids in terms of apart from the life, people are interested in mining the asteroids to or make for various reasons, and also they are also rich in platinum group metals. To a reason, also they could, if we are able to harness the asteroids, for example, for interplanetary trips, we could use we could extract water from silicates in these asteroids and to be self-sufficient and without carrying everything from Earth, because it's also costly and the bigger the mass that you send up from the Earth is the higher the cost you have to pay. Yeah, so there are these different paradigms taking place right now, and I just leave you with, as the time is almost up, I think, with these interesting words from Carl Sagan about the Earth. Yeah, that's it. I think if you have some questions, I will try to answer. Thanks a lot for your time.
Thank you a lot, Dr. Deshapriya. I would like to invite everyone, if anyone has any question, please don't hesitate to ask on the chat or live to our guest. We have a question from Sally Hankash. Is the left-handedness of amino acids on Earth explained by the findings in the asteroids?
Yeah, I think from what I remember, I think, yeah, this is from the meteorites. Well, from the meteorites, we have found the left-handed amino acids in the meteorite samples, but from the asteroids, I'm not sure, because you only have the Hayabusa 1 or the first Hayabusa mission. So these asteroids from the S-type, the samples from the S-type asteroid Itokawa. So this is not exactly the composition we are looking for. So, but I am hopeful the samples that the Hayabusa 2 brought from Ryugu, or the samples that the OSIRIS-REx bringing from Bennu would have them, so to confirm this.
Okay, thank you. Any other question? Okay, I would like to ask if we have proof that maybe we are talking about that the origin of water on Earth, maybe from it comes from comets. What will this change in our understanding of the life of? Okay,
for the water of the oceans, I think it's now more towards the meteorites, because from the Rosetta space mission, we get samples from Rosetta spacecraft, and we also from the comet Churyumov-Gerasimenko, that the D2 or isotopes were away from the values of the terrestrial oceans, and so were the other comets for which we had values visited by spacecraft. So the current understanding is more in the lines of asteroidal origin for the water on the terrestrial oceans, but it would change. Yeah, I think it's a very interesting question. I have to think. I think it's. I think in the first place we could think that these sort of impacts were more like taking place in the initial solar system. So they would have delivered the same material to the other planets, you know, not the Earth, but to the Mars as well. So because this bombardment was taking place at the initial phase. And yeah, apart from this, I can't tell too much about it because I'm not an expert on this field, but I think it will raise some interesting questions, of course.
Okay, we thank you a lot, Doctor, for this. Okay, we have a question. We will have the last question from Muhammad Hamdi. What are the remaining challenges concerning the observation of small objects and reconstructing their 3D shape and trajectory?
Okay, what are the okay, yeah, for the 3D shapes, you could make the 3D model if we have if we still had the Arecibo telescope, which was we were redoing when they were passing close to the Earth. We do some radar observations, and from this you could inverse the data, and we could make a 3D shape model, a very approximative one. But once you are near the asteroid, you can make a 3D model, a very accurate one, using using an altimeter. So which we did with the OSIRIS-REx actually. So you just like send signals and get feedback. So from this you get the 3D model, and the trajectory, of course, it's an interesting question. I think I answered the first part of the question. The trajectory of the asteroid is determined mainly by the Keplerian laws for the planets, but for the asteroids, as I told you, there are this Yarkovsky force. So which is a very interesting experiment you can do if you are nearby an asteroid to measure the thermal inertia correctly, and get its contribution to the Yarkovsky effect, and better predict its evolution. So how it evolve, because this contribution of the Yarkovsky effect dictates if the asteroid is if its semi-major axis were to decay or increase. So just from the Earth, we can do it to a certain extent if you observe it for objects that have very low synodic periods with the Earth. But if you have a spacecraft, of course, you can identify it better using this sort of in situ from the orbital measurements. Yeah. So the challenge is like getting more data, yeah, to sending spacecrafts.
Okay, thank you. This question was from Mark Bouzid. The question from Muhammad Hamidi is, could life formation on Earth come from asteroids? I guess you answered this question, but can we have more details about it?
The ingredients for the life could come from the asteroids. And I think this is the current understanding, actually. And the life to form an asteroid, if it were the point the question is asking, I think because it's all in a vacuum, you know, and you get it like immediately bombarded by cosmic rays and the sun's ionized particles. So I think it will be very hard thing to imagine. But I mean, this is not proven or unproven. You can't say exactly you can't do this, but I will be more inclined to believe that it's quite hard to form a life on an asteroid.
Okay, thank you a lot, Doctor, for this presentation. We will take 5 minutes break before